Hey everyone, welcome to my channel. My name is Ayush Maharaj. I go to the University of British Columbia and I study computer science. So in this channel, I'll be solving coding problems, and maybe as I progress, I'll be also building projects completely live with no script, no spoilers, or anything like that. It'll just be me kind of figuring out the problems as I go. So if you've ever struggled with Leetcode, or you just kind of want to see how a real coder thinks through certain problems, you're probably in the right place. I'm doing this not only to challenge myself with Leetcode and the certain projects that I might be working through, but I also just kind of want to share the raw and honest process of like learning and struggling and improving as you code. So if you want to follow along and learn with me, hit that subscribe button and let's get started. So for today's problem, I'm going to be trying Leetcode 144, binary tree preorder traversal. So I haven't actually tried this problem. As you can see here, I have no submissions, but let me have a look. So given the root of binary tree, return the preorder traversal of its nodes. So that means, okay, 1, 2, 3, that makes sense. Here, okay, here we have 1, 2, 4, 5, 6, 7, 3, 8, 9. Okay, this looks like it's just a depth first search where you start in the left side and you make your way to the right. So I've actually done like a good number of problems, even in trees. I've done few easies and even a few mediums, so this actually doesn't look that bad, but there's probably two ways to solve it. There's the recursive and the iterative approach. Oh yeah, there you go. Okay, cool. Okay, so let's try the iterative. Actually no, let's try the recursive approach first, because that's probably going to be easier. I usually do, with all of these roadmap problems for Leetcode, all of these problems pretty much, I just did it recursively. But let's see if I can solve both ways today. Okay, so first, we probably need a result. Okay, yeah, a result, which is a list, and basically, we should create a depth first search function that goes through, and every single value that it sees, it just adds it to the result, and then it applies the same function to the left and then the right, because you want to start going down the left side. That's what preorder means, I presume. Yeah, okay. So I can't do recursive calls to this function because every time it's going to just reset the result. So I'm going to create a nested depth first function that consumes the root, and it should produce, well, it shouldn't produce anything, but it should just simply add the result until you've hit the base root at the very bottom, where all of them are just resulting in none. So you need a base case. The base case should be basically if you just get like out and you hit no, there's no left or right node. So if not root, just return, and then that means there is a root. If this does not happen, then that means there is a root. So what do we want to do? We want to append it, right? So result dot append root dot val. Okay. Now what we want to do is we just simply call this function on the left and the right. Left and then the right. Yeah, okay, that makes sense. DFS. Right dot left and then. Okay. Does this work? Let me just try this. Just see what this might yield. Okay. Oh. Oh my gosh, how did I mess this up? I didn't even call the function. I just defined it, I didn't call it. This should work now, hopefully. Okay, there we go. Nice, beautiful. Oh, that's awesome. Okay, to try to explain this real quick. So basically what's gonna happen is the result is just nothing. Okay, here I'm gonna put the result as we progress down here. So right now it's just nothing, okay? So what's going to happen is we call depth first search on the root, and it's here. We're at 1. I'm going to do it on this one, not this one. This one's going to be too easy, but this one might be a bit more complicated. So what's going to happen is you're going to append, since there is a root, you're going to append the root value to the result. So you're going to have 1, okay? Now you're going to call this function on the left, right? So you're going to call it on the left, but keep in mind this right is still pending. Once you've completed the entire left function, you're going to get to the right function. So first, that's why you see all of these numbers come before the 3. You see 1, 2, 4, 5, 6, 7, 1, 2, 4, 5, 6, and they all come before the 3, which means that this whole function is called and completed on the 1 for the left root just before you start on the right. So you call it on the left, you have a 2. Okay, this is not going to produce true. So you're going to come here and you're going to append root.val. So you're going to have 2 now. 2. And now you're going to call left again. But keep in mind the root for this one is also pending for the right side. So you're going to go to the left side, and that's also a root. So you're going to have 4 now. Keep in mind this is following along with the output that you want. Then what's going to happen is you're going to see this and you're going to go to its children, and they're both going to have no root, so you're just going to return nothing. Nothing's going to change basically, and then it's just going to go back up here. And keep in mind the right, so that means the whole left side call for this 2 is done. So now you're going to go, you're done this for the 2. Now you're going to go to the right. Okay, the right is going to be 5. And then you're going to call the left here 6, and then you're going to get none here. So then it's going to go back, and the right for this is going to be pending. So now you're going to do the right, and you're going to have this, and then it's going to be none. So you're just going to add 5, 6, 7, 5, 6, 7. Now you're done on this whole side, which means that for the 1 here, you've completed the entire DFS on the root left. So now you're just going to go to the right and do the exact same thing, and this is just simply going to be 3, 8, 9, 3, 8, 9. So that's how you get that answer. Okay, let's see if I submit this, it should work, hopefully. Beautiful, look at that, 100%. Okay, and it goes through every single node once, so it should be O of n for time complexity. Okay, now let's try to do it iteratively. Okay, so generally, okay, I'm just gonna clear this, just see what I can do with this now. So I've solved it now. Okay, so it says, okay, so we probably need 2 lists this time. Iterative approaches usually involve a stack or a queue data structure. So I'm going to have a stack somewhere in there. I'll just define these for now. And then we also want to result. The stack is just kind of the condition that you use to determine if you keep going or you stop the iteration. And then the result is just kind of what you probably want to return. So what I'm going to start with is, how about we do this? So stack could be a list of nodes, okay? And basically what we'll do is we will start with the initial node, okay, the root 1, and then it'll have all of its subtrees, but really all we care about is, yeah, just like that node. And then what's going to happen is, what we should do is we should add the right and the left to this, and we should pop this and add it to the result. That makes sense, because then what's going to happen is you're going to have the left one come in. Okay, the left one's now going to be at the front, and then you're going to add the right first of this, if that makes sense. So first you're going to have, I'll just do like a little quick, so you're going to have 1, right? So what you want to do, let's pretend we have our stack here, okay? And let's pretend we have our result here, okay? So our stack is going to be 1. Okay, this is, I know it says we're doing entire nodes, not just the values, but pretend this is just the node, okay? So we're going to have 1. We're going to add 3 and 2, okay? We're going to add, one sec, actually, one moment. I think what we should do is we should, oh yeah, because we're going to pop. Popping removes from the end of the list. So if we add 3 and 2, it's going to remove the 2, and that's not what we want. So maybe we pop first. So essentially what I'm going to do is, this is our result. So I'm going to remove this, and I'm going to put this here, and I'm going to pop this, okay? Then what I'm going to do is I'm going to add the right and then the left. The reason I add the left next is because we want to work with this term. So then what you do is, now we're looking at this term, okay? And we're going to call this like something, okay? We're going to say n equals to 2, okay? So what we're going to do is we're going to pop it, and we're going to add it to this, okay? Now keep in mind, this is still n. Now what we're going to do is we're going to add the right and the left of n. So that would be the right and the left of 2. So that would be 5 and 4. So now we're going to add 5 and 4. And then we just keep doing the same thing until basically there's no more terms and this completely goes empty, and then we return this. Because notice how we have 1, 2. Okay, I think I just had 3, 5, and 4 here before I deleted it. So if you think about it, the 4 is going to get appended next. You're going to append the 4, and then you're going to remove it here, and then you're going to add the 4's children, but there's none, so you just ignore it and you go to the 5, and you're going to add the 5 now. So you're going to add the 5 here, and you're going to you're going to pop it, and you're going to add its children, so 7 and 6, 7 and 6. And then both of these don't have any children, so you're just going to add them, 6 and 7. You're going to remove these. And you see how this is playing out perfectly. 1, 2, 4, 5, 6, 7. 1, 2, 4, 5, 6, 7. And 3 is kind of just the start of this right subtree here. So that's kind of what I'm going for with that. So let's think. Okay, so we have while stack. That's what our condition was, remember? So it was like while that stack had elements in it, but once there isn't any, then we return. So it'll be like while stack, we'll have something here, and then we'll have a return result. So what we'll have is we'll have like some node, okay, and we'll set it to the stack.pop. This is going to remove the rightmost element of the stack, and it's going to set it to this value. This node is going to be that rightmost node, and it's also going to remove it from that list. So now what we want to do is so we have result. We want to append. Result is a list of integers. So we're not appending the node itself, but we're appending the node value. Okay. Then we simply. So now what we can do is we can just simply add the left and the right child to our stack. So stack.append n dot right stack.append n dot left. Okay. I feel like there's something off about this. Okay, let me try. Oh, oops. Okay. Let me think. N.val. Okay, I think this is a problem in the very first iteration. Because n.val. Yeah, because what if root is none? Then what happens? Because then there's no value for n. So what we probably want is we want like a if not root return. I guess I could say this, but I'm just going to say result since it's already up there. And we'll go ahead and run that and see. If not root, return result. Okay, well, let me try. Okay, wait, hold on. I think there's a problem here too, because if I call, wait, I don't understand how there's a problem here. Oh, sorry. N.val. What even is this? Okay, I think there's a problem here that I'm seeing, is that if there is no right node, so we'd have to say if n.right, and then we'd call that, and then we'd say if n dot left, and then we'd call this. But I don't quite understand. Okay, yeah, see, okay, that was interesting. Why would it say there was a problem here, and then I adjusted the code here, and it fixed it? End up right. Oh, because I was calling this. I was calling this, and I wasn't calling it, but I was appending none, or I was appending none, and then it would loop back here, and then it would be like, oh, well, n is none. I see the problem. Okay. Okay, hopefully this works now. Let's see. Beautiful. Let's compare these. 30, so both of them are 100%. 33.93, 53. So the recursive approach, this is the recursive approach, right? Yeah, the recursive approach seems to beat it in memory. Kind of makes sense, I suppose, considering that there's two, not entirely sure how that works, not gonna lie, but considering that there's two lists here, might have something to do with it, and the fact that you're updating them quite frequently. But yeah, hey, okay. Well, that's going to be it for today's video. Thank you guys so much for watching. I hope you guys enjoyed, and I hope you guys learned something from this. Yeah, going forward, I'm just going to continue to, maybe I'll pick up some harder problems, maybe some mediums, or at least some more complicated problems. This was honestly not too bad. I solved this in 2 different ways pretty quick. So yeah, I hope you guys enjoyed, and I will see you in the next one. Bye-bye.